So let's talk about some principles of counting. If someone throws the word combinatorics at you, they're really just talking about counting things. It's how we count up a lot of things. So here's an example. Let's say we're planning a schedule for next quarter. And there are 4 different sections of stats. Let's say of stats 13. There are 2 sections of biosci 2C. And there are 3 sections of Chem 2A and 2 sections of Music 10. We've thrown in those extra numbers there to make it more confusing on purpose, to make it harder, just because. How many different schedules can you make? Or design? We're making kind of the assumption here that each different section of stats 13 is offered at a different day or time. Like one of them's Monday, Wednesday, Friday at 10. One of them's Monday, Wednesday, Friday at 2. Maybe one of them's Tuesday, Thursday from 3 to 4:30, whatever. They're all different times. So choosing each different section would result in a different schedule. So let's think about what we've got here. So first we're going to choose one of the stats sections to register for. So let's say we pick the first one. Let's call it S1. And then after we make that choice, well, then we have 2 different biosci classes to choose from. Either the first one or the second one. So for each of the 4 different possible stats classes we could choose, there are 2 bio classes we could choose. And if it were just that, how many different schedules could we make if we were just picking those 2 classes? Well, how many different paths are there? So there's 1, 2, 3, 4, 5, 6, 7, 8. Or 2 times 4. Or 4 times 2. 4 choices for the first section of stats, 2 choices for the section of bio. But then we also have to pick a section of chemistry. So for every possible way we've chosen, and actually you should look at everything, right? But I'm really thinking of this as this path is I chose the first section of stats, the first section of biosci. This is the first section of stats, the second section of biosci. Second section of stats, first biosci, second, third first, third second, fourth first, fourth second. So those are all the 8 different ways I could choose one of the stats classes and one of the bio classes. Or sections, I should say, not classes, sorry. But then for each of those 8 choices, then I have to pick a chemistry class. And there's 3 chemistry choices. So I'm going to get 3 more paths for each of these. Which means now I've got 4 times 2 times 3. There are 24 different ways I could pick a stats section and a bio section and a chemistry section. And then after I pick my chemistry section, then I still have to pick a music section. So for each of the chemistry courses, there's either pick the first music section or the second. The first or the second. The first or the second. Times another 2. So this is equal to 4 times 2 times 3 times 2, which is 48 different possible schedules. And this is an example of the multiplication principle. I should have written that on the top. Sorry, I thought I wrote it when I was saying it, but I didn't. This is the multiplication principle. Essentially, if you want to have one of these things and one of these things and one of these things and one of these things, we kind of multiply all those possibilities together to get the total number of possibilities. So this is kind of where the permutations and the combinations come into play. For example, at the library. Which might seem kind of silly. Let's say that there are 5 different chemistry books. There are 4 different math books. And there are 6 different biology books. How many different ways can we arrange the books? On the shelf. And I'm going to employ what I think is a pretty standard thing to do. If you've got a number of things that is relatively reasonable to like draw, like it's not like 50 or 70 or something too big. 15 is kind of at the upper end. I'm going to draw out a space for each of them. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 spaces for my 15 books. And then in each space, I ask myself, how many choices do I have? So for the first book, remembering that all the books are different, how many choices do I have? Well, there's 15 books to choose from. I haven't placed any of them yet, so I have 15 choices I can make. There are 15 different books I can put there. But then I've put one of the books down. So in the next spot, I have less choices. I have only 14 books to choose from. But I do want to multiply those possibilities together because, right, whatever book I choose here, maybe it's one of the math books and then I put one of the chemistry books here, but I could use the same math book for any of the other 14 books there, but then any of the first 15 books could go here. So really, I want any of the first 15 books paired with any of the remaining 14 second books. And then we continue on. There's 13 choices for the third spot. There are 12 choices for the fourth spot, all the way down to 3 times 2 times 1. And of course, we don't want to write all that out because we like writing compact notation. So the number of ways is going to be 15 times 14 times 13 times all the way down to 1, which is 15 factorial. And that actually leads us, well, actually, we'll say one thing before we talk about that. What if we change the problem a little bit? What if all books of the same subject have to be adjacent? Well, okay. So that means we could do all 5 chemistry books first. So if I'm just doing, let's say I want to do chem first, and then math, and then biology. So for the 5 chemistry books, there's going to be 5 factorial ways of arranging them. For the 4 math books, you guessed it, there's going to be 4 factorial ways of arranging those 4 math books. And then for the 6 biology books, there's going to be 6 factorial ways of arranging those biology books. Okay, but who declared that we had to do chem first and then math and then biology? No one, right? We don't have to do it that way. We could do chem, then math, then bio, or chem, then bio, then math, or bio, then math, then chem, or bio, then chem, then math, or math, then chem, then bio, or math, then bio, then chem. But it's hard to list them all out, and we don't have to. How many things, how many subjects am I trying to rearrange? And how many ways are there, or how many ways are there of permuting 3 things? Right. So we're going to take these 3 subjects and say, well, we could do it this way, or this way, or, right, I can't even write them all out, or this way. But really, we should just say what you said, which is, yeah, it's 3 factorial. So we're going to multiply that by 3 factorial to get the number of ways of rearranging the different subjects. So our answer here is going to be 5 factorial times 4 factorial times 6 factorial times 3 factorial. When you're multiplying factorials together, it's not a bad idea to put parentheses around them just so things don't get so messy. And so when you're permuting things, the number of arrangements of n things when order matters. So when order matters, and sometimes it can be hard to distinguish for your own self when order matters. But when order matters, the number of arrangements, also known as permutations, of n things or n objects is n factorial. And then just so you all know this, we do define 0 factorial is defined to be equal to 1. Which is weird, but I promise you in about 10 minutes or less, I'll circle back around to why we need this to be true. So in fact, let me kind of give you an analogy before we get there. So we have, so just don't pay attention to this, right? Ignore this for a minute. I know you all know the additive law of exponents. You might not know it by name, but you definitely know that if I multiply 2 to the third times 2 to the fourth, I get 2 to the what? Right, 7. That's the additive law of exponents, because really 2 to the third is just 2 times 2 times 2, and 2 to the fourth is 2 times 2 times 2 times 2. And how many 2's am I multiplying together? Oh yeah, 7 of them. That's exactly 2 to the 7th. Okay, but because the additive law of exponents is true, right? I shouldn't say it's true. It's a thing in math we decide we want to be true. Math is a system of axioms. We decide on a few things that we're going to be like, okay, everyone agrees these things are true. And then the rest of math is the fallout from that. It's all like rules we get based on things we have assumed to be true. For example, the reason that 2 to the 0th power is 1 is because we want the additive law of exponents to work. And if 2 to the 0 times 2 to the third, well, if I add those powers, what do I get? 0 plus 3, which is 2 to the third, but 2 to the third is 8. So I've got 2 to the 0 times 8 equal to 8. So what does 2 to the 0 have to be? It has to be 1. There's no other choice because we want the rules to work. So and I'll tell you in a minute why this rule is the way it is, but that's why some things are weird, but true, because we've said we want this system of rules that we all agreed upon to work, and then there's all these consequences because of that. This is one of those consequences. 2 to the 0 has to be equal to 1 because the additive law of exponents has to work, at least in our system of mathematics. Okay, we'll come back to this in a minute, I promise. Last time we did a bunch of examples about, well, maybe not a bunch, we did a few examples about the number of ways of arranging the letters in a word. So for example, how many ways, or how many words, although we know they're not words, right? We talked about the word lesson. How many ways can we rearrange or permute the letters in the word, I don't know, let's say golf? Well, there's no repeated letters, so the answer is just going to be 4 factorial. There are 4 choices for the first spot, 3 for the second, 2 for the third, 1 for the fourth. But if we have repeated letters, then things are a little bit wonkier. If our word was instead, say, I don't know, puppy. I heard there are like puppies on campus. I don't know, like my coworker had gotten an email like my wife was complaining, or no, not my wife, my other coworker was like, they don't ever tell us about this. And someone was like, we just got an email like the other day about like there's gonna be puppies on campus somewhere. Now I feel like I owe you all an explanation. I will figure out what I'm talking about later on. That's not it. No, it might have been yesterday. Anyway, next time I hear about puppies, I'll write it in campus. But sometimes they're like puppies on campus, and they're like, come see the puppies. Have a good time. Anyway, there are 5 factorial ways of rearranging these letters, but some of the rearrangements are going to look the same, right? If I think of each P as being distinguishable from each other, then yeah, there's 5 factorial ways of rearranging these 5 letters. But the problem is there are 3 factorial ways of rearranging those 3 P's, and a word would still look the same, right? This word and this word and this word and this word. I'm gonna write like 6 times, and this word. You get the idea, but I'm almost done. So, and this word. They would all count as a different permutation because I'm thinking of my P's as being different letters, but then I'm saying they're really not. Right? I'm saying in my original setup where I'm thinking of P1 and P2 and P3 all being different, those would all look like different words. But now when I take away that rule, that idea, I say, oh, all these look the same. I don't want to overcount by 3 factorial. So I'm going to divide by 3 factorial the number of ways I can reorder the 3 P's that are all looking the same. Oh, there's another good word here too. Let's do one more. So after you know how this works, it's pretty easy. How about statistics? Ugh. Okay, how many letters are in statistics? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. I think, right? Statistics. My I's and my T's are a little bit dicey there, but they are, yeah, okay. So there's 10 factorial ways, but then we have to divide by the number of ways you can rearrange any double letters. So let's see, there's 3 S's. So we need a 3 factorial. There's 1, 2, 3 T's. So we need another 3 factorial. And there are 1, 2 I's. So we need a 2 factorial. If you really, really wanted to, you could also throw in a 1 factorial for A and a 1 factorial for C. But that's not going to change anything because 1 factorial is just equal to 1. Oh, let's see. Yeah. Yeah. All right. Whatever that is. Yeah, sure. Okay. Oh yeah, and so just kind of go with that again. If I want to find for a group of 7 people, how many ways can we award a first, second, and third prize? Well, again, I'm not thinking about this formulaically almost ever. I'm thinking about how many choices do I have? Okay, for first place, how many different people could be first? 7. Well, then after I've chosen the first place person, then I only have 6 choices left for whoever's going to be second place. It doesn't mean that any 7 of the people couldn't be second place. It just means that I picked one of us to be first, and then after I picked the one of us, the other 6 get to vie for second. But maybe I picked a different person for first, and then the person who was the first place choice now it could be an option for second place with a different choice. And then finally, a 5 choices for the third place position. So that's gonna, and I would really, if it were me, I would probably just write my answer like this. But I will point out that this could be also written as 7 factorial divided by 7 minus 3 factorial. The reason I'm writing it like that and not just saying 7 factorial over 4 factorial is because I really want to emphasize that from the 7 people, we are picking 3. So I have 7 factorial on top and I have 7 minus 3 factorial on the bottom. And this is the number of ways of permuting 3 people or things from a group of 7. More generally, and here we're going to have another formula, the number of permutations of k objects chosen from n objects, from a group of n objects, is, then there's like 3 ways of writing this. None of them are good. P of n comma k, or P n k, and it's equal to n factorial over n minus k factorial, just like we did up here. Does anyone have a calculator on them? Just curious. So if you're curious, I can show you how you actually like can calculate this on your calculator. It's kind of neat. Yeah, let me borrow that for just a second. This I think you all maybe we'll see if we can see it here. Just so everybody knows, if you're actually trying to find the number and not just like 7 factorial over 4 factorial is something you could totally just leave as the answer. But I want to point out that if you have a calculator like this, if you want to do 7, how many ways of permuting 3 things out of 7 things, you would hit 7. Then you would go to the probability button. You go over to NPR, apologies, NPR. Hit enter, then hit the 3, and then equals. And you get 210, which is exactly 5 times 6 is 30, 30 times 7 is 210. Oh yeah, that's exactly the right number. So that's how you do that. And it's nice when you have to, if you actually need to find the number for larger numbers, it's a relatively easy way of doing the calculation. It's also nice because sometimes you might want to do something like that seems like it should be doable, but the top part, like if you try and do it separately, like if you try and do like 20 factorial divided by 10 factorial, your calculator might be overwhelmed by 20 factorial. It might be too big for it to calculate. Where 20 choose 10 is the calculation it can actually do because you kind of are getting smaller before you get bigger. Yeah. All right, so permutations, the thing you need to remember the most about permutations is order matters. We care what order things are in, like who finishes first, second, third in a race, what order you listen to the songs in on your playlist is a common example where order does matter. Things like that. I'll give you this back, but I'll show you that. On the other hand, combinations, order does not matter. Oops, oh, that's interesting. Oh, interesting. There's a circle back there. Combinations. It might be before your time, which is kind of silly to say. Whenever I say the word combinations, I think of I'm at the Pizza Hut, I'm at the Taco Bell song. You guys know the one, the Pizza Hut Taco Bell combination song? I mean, it's not a good song, but it's a great song. So yes, combinations, Pizza Hut, Taco Bell. We did this example already, but we'll change up a little bit. So how many let's say permutations first. How many permutations, not combinations, of 3, no, let's say 2 letters chosen from A, B, C, D, E, let's go F, are there? Well, how many ways can I permute any 2 letters? Well, let's just ask ourselves the easy questions. If I care about order, how many choices are there for the first letter? I mean, how many letters do I have here? 1, 2, 3, 4, 5, 6. There are 6, and then for the second letter, 5, which is 30. And we could list them all out, right? It would be A, B, A, C, A, D, A, E, A, F, and then B, A, B, C, etc., all the way to F, A, F, B, F, C, F, D, F, E. That would be all 30 combinations. Permutations, apologies. All 30 permutations. But I want to point out, we are double counting just the number of combinations, right? The combination AB is coming up twice. The combination AC is coming up twice. It would be like right there or right there in your C row, right? CA, CB, CD. The combination AF is coming up twice. If I don't care about order. If I don't care about order, but I know permutations do care about order. If I didn't care about order, these would be double counting AF. These would be double counting AB. These would be double counting AB. So if I care about the number of combinations, combinations of two letters chosen from A, B, C, D, E, F. Basically, here's the easy way to say it. The number of combinations of K things out of N things or whatever is the same as the number of permutations, but then you divide by the number of ways of permuting those things. So you divide by, in this case, 2 factorial, or in general, you divide by K factorial. So here, and actually, let me write this more here. This is equal to 6 factorial over 6 minus 2 factorial. I'm going to take that answer and I'm going to divide those number of permutations by 2 factorial to avoid the double counting. So the number of combinations here is going to be 6 factorial divided by not just 6 minus 2 factorial, also 2 factorial, which will be 15. Which you could totally list, right? AB, AC, AD, AE, AF. I've already done AB, so BC, BD, BE, BF, CD, CE, CF, DE, DF, FE. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, all 15 of them. So the number of combinations of some number of things out some number of things is just the number of permutations divided by the number of ways of permuting however many things you picked. In this case, we divided by 2 factorial because we were dividing by the number of things we picked, which was 2 factorial, which is the same as 2, right? 2 factorial is equal to 2, but we say 2 factorial just to be more general. So we're almost back to why 0 factorial has to equal 1, just so you're all ready for it. For some reason, the permutation idea doesn't have a nice notation for it, but the combination notation has a very standard notation that goes with it. So if I want to find the number of combinations, wow, I can't spell. Let's try that again. The number of combinations of K objects chosen from N objects is, and there's probably a couple of good ways to write it. You can write it as C N comma K, or C, I think I forgot that one in the previous one, C of N comma K, or C N K, or the preferred notation, N choose K. That is how everyone wants you to write it. If you have a choice, that is how you should write it. And it is equal to N factorial over N minus K factorial as well as K factorial. And notice, right, this is literally just equal to the permutations. Right, this is what we want. But really, I just want to point out, it's equal to the permutations divided by K factorial. Kind of cool. Okay, so now let me ask you a question. How many ways are there of picking 1 finger out of 5 fingers? How many different fingers could I pick? 5, right? 5 choose 1. Let's see, take a look here. So how many ways can I pick 1 finger out of 5? The answer is 5 choose 1, and that's equal to 5 factorial over 5 minus 1 factorial times 1 factorial, which is 5 factorial over 4 factorial. I don't really need to write the 1 factorial because it's equal to 1. And that's going to be 5 times 4 times 3. I know I'm doing a lot of math here to get an answer we already know. Don't worry, there's a point. All right, let me ask you a different question. It's, again, going to have an obvious answer. How many ways can I pick all 5 fingers from 5 fingers? 1. There's 1 way I can pick all 5 fingers. I pick all of them. I also want to point out, here's another question, which feels harder to answer, but the answer is the same. How many ways can I pick none of my fingers? 1 way. There's one way to pick none of your fingers. You pick none of them, which always feels a little weird, but that is true. Okay, so look at the math. If I want to pick 5 fingers out of 5, well, it's going to be 5 choose 5. Now watch. 5 choose 5 is going to be 5 factorial over 5 minus 5 factorial, and then also 5 factorial. Well, the 5 factorials will cancel. 5 factorial divided by 5 factorial, those just go away. So I'm left with 1 over 0 factorial. But we know this answer needs to equal 1. And for this answer to equal 1, it better be true that 0 factorial is equal to 1. Otherwise, we're going to have real problems. So this is one way of showing you why we need 0 factorial to be defined to be equal to 1. Because if it's not, then everything else we're doing kind of falls apart. So this is a way to show, or we just showed, that 0 factorial needs to equal 1. So at least now you can be a little bit convinced that, oh yeah, 0 factorial is equal to 1. So you probably won't run into it much, but you can run into it. It's also worth noting here that 5 choose 5 is the same as 5 choose 0. Equal to 5 factorial over 5 minus 0 factorial times 0 factorial, which is literally the same thing as above. There is this symmetry in the choose function where you can always think about choosing the number of things you want or choosing the number of things you want to exclude. And I think I talked about this last class a little bit. You can either choose, there are 5 ways of choosing one finger, or there are 5 ways of choosing the 4 fingers you don't want. Same thing. You can always choose the ones you want or the ones you want to exclude, and it's going to give you the same number. Yeah, let's see here. Cool. So then things just get messier. How? Let's see. But we want to. Let's see. We have. So next week is the last week of class, right? Right. Has she talked about? Probably not. Why am I? So the plan for us is going to be talk about probability today. We'll probably just talk about probability every day. Thursday we might review generally, or we might just still talk about probability because you might want to be talking about probability. Your final is cumulative, right? But I imagine it'll be more, not maybe more heavily, but certainly I imagine the probability, the chapter 12 stuff will play a larger role in it than it would be if it was just equally distributed among the whole quarter. So there's definitely going to be some probability on this test. Combinatorics, probability, same idea. So yeah. Sure, we'll talk about a couple more of these, but I feel like we should move along to the actual, because right now all we've talked about is counting. Combinatorics, the number of ways of counting the number of things you've got, which we need to then answer probability questions, which we are going to get to in the next 15 minutes. Well, let's do at least one more of these. So let's look at this example. A jar contains 5 green. I should use my colors, but I don't want to. 4 red and 3 blue marbles. How many ways? So we randomly, without looking, grab 3 marbles. How many ways could we get all green? Which, when you first read it, might sound like a dumb question. Because you're like, well, James, there's only one way. They're all green. But we have to remember that there's, like, so maybe imagine that there's 5 green marbles, but they are not all like exactly the same looking. Like one of them's like swirly this way, one of them's got like speckles on it, right? You've got 5 different green marbles, but they all look like different patterns. One of them is checked, one of them is camouflage, I don't know, but they're all different. So you could pick these three green ones or these three green ones, and it would, even though you're still getting three green, it's a different way of choosing those three green ones. Now, order doesn't matter here. I don't care which one I pull out first, second, or third. In fact, I'm just going to grab three at once. So I want to know how many different ways I can get three green ones. Well, out of the 5 green ones there are, I'm trying to choose 3 of them. And that's my answer. Oh, by the way, if you want to do this on a calculator, same idea. You would do 5, you would hit probability, you would hit NCR for the choose function, and then 3. And it should be 10. And it is, because it's equal to 5 factorial. Now I'll point out, I've been writing 5 minus 3 down here and 3, but really I'm just going to do 3 factorial and then whatever the difference is, which is 5 minus 3, which is 2 factorial. That's how people typically write it down. Like, oh yeah, I've got a 5 on top, I've got a 3 on the bottom, and then the difference between them is 2. And then that ends up being 5 times 4 times 3 times 2 times 1. But you don't have to do all this work because we know from the calculator this is equal to 10. 20 over 2 is 10. Oh yeah, good works. Also, just so you all can see this, in this section here, it might be easy to miss, but in the probability part, there's also a factorial button. And then there's some other weird stuff. Thank you. What if I wanted all black and, oh, sorry, not all black, all blue? Well, now there is only one way, right? There are 3 blue balls and I want to choose all 3 of them. So 3 to choose from and 3 that I want to choose is going to equal just 1. And that's always true. If you're trying to choose all the things that you have, there's only one way to do it. You choose all of them. What if we wanted one of each color? All right, so now things are getting a little more interesting. How many ways? So I want to choose one green one, and there's 5 different green ones to choose. So there are going to be 5 choose 1 ways of getting the green marble times 4 choose 1 ways of getting the red marble. Oh, I should say a red marble, right? There's many to choose from. Times 3 choose 1 ways of getting one of the blue marbles. I do think it is worth knowing the following easy facts, because there are some simplifications you can do that are easy. So just so you all know, n choose n, like we just said, is 1. N choose 0 is also 1. N choose 1 is n. The number of ways of choosing one thing out of n things, there are n ways of picking one of them. 1 finger out of 5 fingers. There's 5 ways of picking 1 finger out of 5 fingers. And then, because of symmetry, the number of ways of choosing n minus 1 things out of n is also n. If I want to choose 4 fingers out of 5 fingers, there's 5 ways of choosing the 1 finger I don't want. The reason I bring this up is because all of these things here, this is really just 5 times 4 times 3, right? I don't want to write out 5 factorial over 1 factorial times 4 factorial times 4 factorial, right? That's too much writing. When we have things that are easy like this, we're going to say, oh yeah, that's going to be 5 times 4 times 3, which is 60. A few more. Don't worry. I mean, I would say don't worry, there's a point, but there's always a point. But we're going to come back to this in a little bit and talk about how we talk about probability. What if I wanted 2 green and 1 red? Well, how many if there are, let's see, how many green ones are there? 5. There are 5 green ones. How many ways are there of choosing 5 green ones out of 2 green, or 2 green ones out of 5 green ones? And really the words almost tell you what the answer is. If I have 5 green ones and I want to choose 2 of them, order doesn't matter. 5 choose 2. And out of the 4 red ones, I want to choose 1 of them. It's 4 choose 1. But I don't care if it's these 2 green ones with that red one, or these other 2 green ones with that red one, or these other 2, right? So that's why I multiply them together, because any 2 green ones with any 1 red one will work. And there are 10 ways of picking 2 green ones, because 5 choose 2 is 10. And there are 4 ways of picking 1 red one. And so any 2 greens with any 1 red, there's 40 different ways we can do that. I like this next question. So 2 more, and then we'll move on. What if I wanted no green ones? Well, how many not green marbles are there? How many marbles am I still trying to pick? Every time I'm picking, sorry, I actually have been specific. I want to pick how many marbles? 3. Out of, in this case, 7. So there are 7 not green marbles to choose from, and I want to choose 3 of them. Okay, and this last one is one that's, I think, a little bit tricky. What if I want at least 1 green marble? Well, here's where things get extra tricky. There are 2 good ways. There are 2 ways of doing this, and I'm going to show you the harder way first, so you can appreciate the easier way, because the easier way is worth appreciating because you will use it. So, at least 1 green marble means I could pick 1 green marble and 2 others, or I could pick 2 green marbles and 1 other, or I could pick 3 green marbles and no others. So there are 5 green marbles to choose from. There are 7 other marbles to choose from. So doing it this way, 1 green, there are 5 choose 1 ways of doing that, times 7 choose 2 ways of picking 2 other marbles. Plus, we're going to add, because these are distinct things, right? I want 1 green marble. So I should point out, there are 2 words we use a lot when we talk about combinatorics, counting, probability, whatever. They're the words and or. If I want 1 green marble and 2 other marbles, I multiply those numbers together to find the number of ways. If I want 1 green marble and 2 others, or 2 green marbles and 1 other, or 3 green marbles, then I'm adding those things together, because we add them to this or that or that. And that's really, there's not like a better way of saying it, I think. It's just kind of, it's the words make it make sense, I think. Maybe, I don't know. 2 green marbles and 1 other, it's going to be 5 choose 2 times 7 choose 1. And 3 green marbles, or 3 green marbles and no others would be 5 choose 3. And you could throw in a 7 choose 0 if you really wanted to there, because we know 7 choose 0 is 1. Let's calculate this, because we're going to do it another way. We want to see if they're the same. So this is going to equal, let's see, 5 choose 1 is 5. 7, something choose 2 is fairly easy to do. When you do something choose 2, it's 7 times the number less than it divided by 2. So it's 7 times 6 divided by 2, which is 42 over 2, which is 21. Yeah. Plus, it's also called like the handshake number, because it's the number, if you have 7 people, it's the number of different handshakes that take place, because you're thinking about the number of ways you can pick any 2 people to shake hands. And then 5 choose 2 is going to be 5 times 4 divided by 2, which is 10. 7 choose 1 is 7. And 5 choose 3 is the same as 5 choose 2. Because instead of picking the 2 people I want, I'm picking the 2 people I don't want. So 5 choose 3, or the marbles, sorry, marbles, not people. 5 choose 3 is also 10. And 7 choose 0 is 1. All right, and that adds up to, let's see, that's 105 plus 70 plus 10 is 185. Okay, let's see if that's the same as doing it another way. So what if this had been more terrible? Meaning, what if I was picking, say, 10 marbles out of 30, and I said I wanted at least 1 green. So 1 green or 2 green or 3 green or 4 green or 5 green or 6 green, up to however many green there are. That's a lot more calculating. And so often when someone says, I want at least 1 of these things or something like that, we say instead, well, instead of counting all the ways of getting what I want, I'm going to calculate the total number of ways of getting anything and subtract off the number of things I don't want. So we could say at least 1 green is the same as the total number of ways of picking any three minus the number of ways of getting no greens. Because that'll leave us with only ways that had at least one green. If we take all the ways of picking 3 marbles and subtract off all the ways of getting 0 greens, then every way that remains will have had at least 1 green in it. All right, let's do it. So the total number of ways of picking any 3. Well, if I'm picking any 3, I don't care if it's red or blue or green. There are 12 marbles to pick from. So that's going to be 12 choose 3. Minus, we already know how many ways they're picking no greens. We did that up here. It was 7 choose 3. So I don't know what these are off the top of my head. Let's use a calculator. Actually find out. This is where it's super useful. So 12 choose 3 is 220. And 7 choose 3 better be 35. I'm in trouble. 35. All right. So there's another way of calculating the same thing, which is, I think, easier, at least more generally, right? If you're trying to do this, it's usually easier to do, oh yeah, the total minus this one thing I don't want versus adding up all the different ways of getting the thing I do want. Okay, yeah, that's all trash. It's not trash. There's lots more counting. We'll probably come back to more counting, but I kind of want to start talking about probability because that's where we're going. So here's the real difference between counting and probability. Counting, you're counting up the number of ways of getting something. On the other hand, let me ask you, if I had said instead, in fact, let's just write it up here. If I had said, if I pick 3 at random, what's the probability of not getting any green? So the probability of something happening is the number of ways of the thing you want happening divided by the total number of things that can happen. Sorry, I feel like I said the word number too many times there. But probability is just the number of ways of getting what you want divided by the total number of ways of getting anything. In this problem, that's going to be 7 choose 3, the number of ways of getting no green marbles, divided by 12 choose 3, the number of ways of getting any 3 marbles. Which in this case, since we know what those are equal to, that's going to be 35 over 220, which reduces to, I think, 7 over 44. Which is some terrible decimal. It's like 0.18 or 0.17. I don't know, something like that. But it's a probability. It is the likelihood of getting no green marbles if we just pick 3 at random. And so that is the prime difference, really, between probability and counting things, is you're just taking the number of ways of getting what you wanted and then dividing it by the total number of things that can happen. So let's look at some other examples here. Let's look at this classic example. A fair coin is flipped 4 times. Or if you prefer, you can think about flipping 4 fair coins at the same time. Question. This is totally off topic. When I say a fair coin, what kind of coin do you imagine? Or do you imagine one? I'm really curious, like genuinely. But like, what do you think of, like a dime? Like, I have a very clear picture in my head of what coin I am thinking of. I'm curious if you too. Yeah, you? Quarter, for sure, 100%. Okay, I was just curious if people. I'm curious. I'm curious with other students if it's also a quarter. Anyway, not important, but I'm very much imagining George Washington's head, and on the back the eagle with, well, like the old school quarter, like the ones that had the bird on the back. But yeah, interesting. Okay, not important then. Any coin will do, but the quarter is what we're all imagining. A fair coin is flipped 4 times. We're going to list what's called the sample space. So the sample space is basically just the list of all the different outcomes that can occur. And it's typically called omega. So let's see what we've got here. Well, one thing that could happen, and usually when you're trying to list this out, if you're asked to list it out, you want to be systematic about it. So we're going to be systematic by ordering it with the number of heads. So you can get all 4 heads. Heads, 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 heads. Right? For the first flip is heads, the second flip is heads, the third flip is a heads, the fourth flip is a heads. Or we could have flipped 4 coins and ended up with 3 heads and 1 tails. And it could have happened as either heads first, heads second, heads third, then tails, or heads first, heads second, tails third, heads fourth, or heads, tails, heads, heads, or tails, heads, heads, heads. And those are all different events because we got the things in a different order, and order does matter, at least for the moment. 2 heads is always a little challenging. So we could have heads, heads, tails, tails. We could have, so here's the system I'm using to do this. I'm starting with heads, heads, tails, tails, and I'm gonna let that second head jump to the right each time until it can't. So I'm gonna do heads, tails, heads, tails, and I'm gonna do heads, tails, heads, heads. Tails, heads. I always make that mistake. And then this H has moved as far right as possible. So I'm gonna move the other H over 1 and move the second H back as far as possible. So I'm gonna go tails. That head moves there. This H backtracks all the way to there, and I start the process over. So then I'm gonna move that H1 over, and then I'm done. So Ted tails, Teds, Ted tails, tails, heads, tails, heads. And then finally, we have tails, tails, heads, heads. I will point out, well, no, I'll point that out in a minute. If I want 1 head, it's the same as getting 1 tail. So what I'm really going to do is I'm going to look at my 3 heads list over here and just interchange the heads and the tails. So I'm going to write tails, 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 heads, tails, tails, heads, tails, tails, heads, tails, tails, heads, tails, tails. And finally, 0 heads is 4 tails. Here's what I would like to point out. The number of ways of getting 4 heads. How many ways can I get 4 heads? Right. Also known as 4 choose 4. How many ways can I get 3 heads? Which is 4 choose 3. How many ways can I get 2 heads? 1, 2, 3, 4, 5, 6. And you can verify that 4 choose 2 is equal to 6. And similarly over here, 4 choose 1 is equal to 4. 4 choose 0 is equal to 1. This seems like a good time as any to remind you of a cool thing. Have either of you seen Pascal's triangle? Oh, look. 1, 4, 6, 4, 1. And it is literally the case that every number in Pascal's triangle is a choose function number. So all these numbers here are 4 choose something. 4 choose 1, sorry, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. The row above it are all 3 choose something. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. It's kind of neat. I don't know if it's super important, but I think it's important. So, anyway. All right, so what is the size of our sample space? Well, how many things are in it? 1 plus 4 plus 6 plus 4 plus 1 is 16. But a better way to have counted that would have been to say, okay, if I asked you if I flip 4 coins and how many different things can happen, you would say, well, James, there for each coin, you have how many possible outcomes? 2 times 2 times 2 times 2 is 16, which is the same as 1 plus 4 plus 6 plus 4 plus 1. All right, so we have all the things, and now we're going to ask a question, and we should introduce some notation as well. So typically when we talk about probabilities, we talk about events. So we're going to say that A is the event of flipping 2 heads. And then we're going to ask, what's the probability of event A occurring? Here's the notation for that, which is very common. We're going to write this as P, capital P of A. That's the probability of A. And it's the number of ways that A can happen divided by the total number of things in the entire sample space. I don't think you need to ever write this notation I just wrote here. This second part, you should, like, I would never ever write that really. I would just say it's the number of ways of getting 2 heads, which is 1, 2, 3, 4, 5, 6, divided by the number of ways I can flip 4 coins, which is 16. And I would reduce that to 3/8. So I would say that the probability of A occurring is 3/8. All right. There's a few more examples in this question here. Let's suppose B is the event of flipping 3 heads or 4 heads. All right, so if I just look at my list here, the probability of B should be something over 16. How many ways are there of getting event B to happen? You can count on one hand. I think it's 1 plus 4, 5. That's our probability. Something to notice, whenever you're calculating a probability, it should always be less than or equal to 1 or 100%. You can't have a problem, at least in math. Like you say, you give 110%, or like if you have earnings for a year, it can be over 100%. But as far as like percentage of a probability as a percentage, has to be less than 100%. Cannot be greater than 100%. It can be equal to 100%, but not greater than 100%. It also has to be non-negative. You can never have a negative probability. So you can't say the probability of something happening is negative 30%. That's just not a thing in math. Okay. So we'll do one more. Let's let C equal the event of flipping at least 1 head. Meaning 1 head or 2 heads or 3 heads or 4 heads. So the probability of C is going to equal the probability of 1 head plus the probability of 2 heads plus the probability of flipping 3 heads plus the probability of flipping 4 heads. And the reason we're allowed to add these together like this without having to really think about it is because they're all disjoint. You can't flip 1 head and 2 heads at the same time. It's either one or the other. So if things don't overlap in any sort of way like that, we can kind of say, oh yeah, we're just gonna add them all together. And there's a little more to say about that, which we'll get to not today, but later. All right, the probability of flipping 1 head was, oh, you know what I forgot? No, I didn't forget. Sorry, I forgot. Was I think 4 out of 16. And the probability of flipping 2 heads is the number of ways is 6 out of 16. And then 3 heads, there are 4 ways out of 16. And the number of 4 heads is 1 way out of 16. If you add that all up together, I think it's equal to 15 out of 16. And even though this example is fairly tame, it would have been easier to find the probability of C by finding instead the total probability, which is 100%, minus the probability of not getting C, which is 0 heads. 0 heads is everything that isn't at least 1 head. And the probability of 0 heads is 1/16. And 1 minus 1/16 is 15/16. This idea here, where you can calculate, instead of calculating what you want, you can do the total minus the probability of what you don't want, is the idea of what's called a complement. The two things are complementary if their probabilities add up to 100%, but they don't overlap at all. So no heads versus at least 1 head, those are complementary. They don't overlap at all, and they encompass every possibility. All right, let's see, what time is it? Okay, we got 15 more minutes. So let's do a couple more examples. Oh yeah, question. Mm-hmm. Mm-hmm. I would say I would say more the key idea is order mattering versus not mattering. So someone, and again, the order mattering ones are like, they'll usually be fairly descriptive. Like you have the examples I come back to are running a race where the order, right? We care what places people finish in, or like seating people in a row. We care what order they're seated in because I am not the same as you and you are not the same as me. So putting you first versus me first is a different permutation. On the other hand, if we're trying to, like, say, choose a group of 3 people out of 7 people, we don't care what order we choose them in. We just care about what the grouping is at the end of the process. And people, for some reason, people seem to feel like playlists order shouldn't matter. But if you're choosing songs, the order you play them in definitely matters, right? People definitely, right? When someone puts out an album, I know albums are like an old thing. When someone puts out an album, right, they have definitely thought about the order those songs go in because it's meaningful. It definitely gives you a different vibe if you start off with the middle track as opposed to the first track. So definitely for playlists, order matters. Basically, if things are distinguishable from each other in an order, then order matters. And it can be hard to kind of get a real firm grasp on that, but with practice, it can become a little bit easier. Which always feels, I mean, let me ask both of you, do either of you have to take stats at some point? You already took it. All right. So really, right. So this feels very much at the end of like, well, okay, we have to do this thing for like a week and a half, and then you might never do it again. But for this week and a half, and then your final, you have to be like, okay, well, we're gonna suck it up, and then maybe never again. Maybe not. I don't know. I don't know what other classes you have to take, but it might not come up very much. Correct. Okay. Right, when it's looking for a combination, I'm just asking for, so like if I was eating 2 flavors of ice cream on an ice cream cone and I didn't care which one was on top and which was on the bottom, I'd say, oh, there's 31 flavors to choose from, and I'm going to choose 2 of them. There's 31 choose 2 ways of getting 2 flavors on my cone. And they could be the same flavor. Could be the same. No, they could not be the same if it's 31 choose 2. In fact, let's write it down. 2 flavors out of 31. Let's look at 3 different treatments of this, maybe 4. I don't care what's on top. But they need to be different. I don't want the same flavor. What a waste. But they must be different. So here the answer is going to be 31 choose 2. Because out of the 31 distinct flavors, I am trying to choose 2 different ones. But I don't care what order they go in. So I don't care if it's chocolate on top, vanilla on the bottom, or vanilla on top, chocolate on the bottom. I'm going to count those as the same. What if I did care which one was on top? Now I care. I want to eat the vanilla first, not the chocolate. How many choices? But I still want different flavors. All right, now how many choices are there for my Well, so for me, the permutation formula is just like not one I ever remember. I just start thinking about if order starts to matter, I always start thinking about how many choices do I have for the thing in this spot? Because being in this spot actually matters now because I'm saying order matters. Well, in the first spot, how many flavors do I get to choose from? Right, because we're going to Baskin Robbins, obviously, where they have 31 flavors. And then for my second flavor, which cannot be the same as my first flavor because I don't want two of the same flavor, how many choices? Right. And that's exactly twice as much as that. Because this is double counting those because vanilla over chocolate or chocolate over vanilla is getting counted as two different things, and here it's not. I could, if I wanted to go from here to here, I could do it that way, yeah. Or I could just do this, right? But this really is, right? This is 31 factorial over 2 factorial times 29 factorial. But 31 factorial over 29 factorial, most of the numbers cancel out, and you're left with 31 times 30. So this is really equal to 31 times 30 over 2 factorial. But 2 factorial is just 2. Oh, look. This number here of combinations of two flavors is half as many ways as just the permutations of two flavors. There will almost always be more permutations of some things than combinations of some things. Because permutations, we care about which order you place them in, whereas combinations, we don't. Yes. No, go ahead. So this is so basically this is counting vanilla chocolate and chocolate vanilla as the same. I haven't distinct like you. I could have said, "Give me vanilla and chocolate." You're like, well, "Okay," and I didn't tell you which way I wanted them. And the scooper is to be like whatever they want, and either answer is fine with me. I don't care what you gave me. I just said vanilla and chocolate. You said pick two flavors. I said I'm gonna pick pralines and cream and Jamil almond fudge. Right? I picked two, and it didn't distinguish. So there's this many ways of picking two, without telling you which one goes on top and which one goes on the bottom. Or there's this many ways of picking two and telling you which one goes on top and which one goes on the bottom. Here, I'm counting vanilla over chocolate as a different combination than chocolate over vanilla. I have told you I want vanilla on top and chocolate on the bottom, or vice versa. And that's counting those two things each get counted once. Whereas they on the bottom one, right? This here has twice as many, right? If you multiply this out, you get 930. And if you multiply this out, you get half of that, which is, I don't know, 465. So, right, I'm only getting half as many ways here because I'm not counting vanilla over chocolate and chocolate over vanilla. I'm only counting one of those, and then the other one is just getting already ignored because I've counted it already. Now, just to make it even more interesting, what if I decide to do something stupid and say, well, maybe I'll get the same flavor on top and the bottom? Flavors can repeat. And I think you have to care about order if you're talking about flavors repeating, because otherwise it'd be weird. So flavors can repeat, and we care what order they go in. We care which one's on top. How many choices do I have for my top scoop? Still 31. How many choices do I have for my bottom scoop? Still 31, because I can repeat the flavors. I get chocolate, or vanilla, vanilla, or two of whatever I want. So here there are 961 different ways to get it. And what's interesting, if you think about this, is it makes sense that there's how many more choices are there from here to here? Right, because there's the 31 doubles. Chocolate, vanilla, vanilla, praline and cream, et cetera, et cetera, et cetera. Cool. What time is it? Yeah, sure. I feel like it's time to stop. I feel tired. Can we stop? Yeah, ice cream sounds great. It says kind of cold, but yeah. Let's call it a day. Next week, we will talk more about probability. So the plan for next week really is to talk about Bayes' formula specifically. Because Bayes' formula, so there's this idea of what's called conditional probability, where I say like, what's the probability of rolling a 3 on a die, given that I already told you I rolled an odd number? Well, that's different than this, right? If I just said, what's the probability of rolling? Well, okay, I'm gonna write this. Sorry. I know I said we're done, but now I started thinking about what we're doing next week. One more second. Sorry. So 6-sided die, real quick. 6-sided die. 1, 2, 3, 4, 5, 6. What's the probability of rolling a 3? 1 out of 6. What's the probability of rolling a 3, given that I've already told you, given that you know we rolled an odd number? Well, what are the odd numbers that we could have rolled? Okay, so 1, 3, 5. If I know I rolled one of those and they're all equally likely, what's the probability that having rolled one of those, I rolled a 3? 1/3. So the idea here is that conditional probabilities change the probability. If you know some of the piece of information, it changes the probability of getting the thing you want. That's what we're going to do next week. And there's this specific thing called Bayes' rule or Bayes' formula, where you start with a conditional probability. For example, like the probability of having testing positive on a test, given that you have some disease, because we design tests to work, right? Not every test is perfect. Your test might have like a 98% chance of giving you a positive result, given that you have the disease. Sometimes you get a false negative, sometimes you get a false positive. But that's not helpful, right? As a patient, I don't want to know what the probability of getting a positive test if I have the disease is. I want to know what the probability is that I have the disease if I had a positive test. And so we're going to find the formula to be able to find the probability of having the disease, given that there was a positive test, based on knowing this and maybe one other thing, which is kind of neat. And the kind of cool thing or interesting thing is that they don't have to be close to each other at all. Like you might incorrectly think that the probability of having since the probability of like, let's say the probability of testing positive, given that you have the disease, was 98%. You might think that then if you test positive, that means there's a 98% chance of you having the disease. And that is not true at all. The probability that you have the disease actually typically much, much lower than that, which is kind of interesting. Yeah. It is, is it one? Yeah, it's 1/3. No, it is the number of ways of getting what you want. So well, in fact, okay, here's actually the real formula. It's the probability of rolling a 3 and rolling an odd number. Well, there's only one way of doing that. You rolled a 3. Divided by the probability of rolling an odd number. Okay, what's the probability of rolling a 3? 1/6. What's the probability of rolling an odd number? 3 out of 6. Those 6s definitely cancel. But honestly, that's not really the way I think of it. What I really think of is, well, if I know I rolled an odd number, my new smaller sample space is the space consisting of the numbers 1, 3, and 5. So then I'm asking, okay, what's the probability I roll a 3 if I only have 1, 3, and 5 to choose from? Well, there are 3 choices, and I'm doing one of those 3 things. Conditional probability like this is always a little bit interesting because it's usually easier just to think of like, well, what's the new smaller world you are looking at? And in that new smaller world, what's the probability of getting what you actually wanted? What time is it? Sorry, we're gonna go. But now I have things to say. So let me give you one more example, and then we'll call it a day because we'll be out of time. So let's say we're rolling 2 die. Dice. Come on, James. 2 dice. And we are told that we roll. Sure. We are given that the sum of the dice, or the pips are what the little things on the dice are called. The sum of the pips on the two dice is less than 7. So we could have rolled like a 1 and a 5, or a 1 and a 4, or a 1 and a 3, or a 1 and a 2, or a 1 and a 1, or a 2 and a, oh, not a 2 and a 4, or a 2 and a 3. Normally we wouldn't write all these out, but 2 and a 1, or a 3 and a 3, or a 3 and a 2, or a 3 and a 1, or a 4 and a 2, 4 and a 1, or a 5 and a 1. And I am considering, right, I'm thinking to make this easier on my brain, I imagine the two dice being different colors. So the first die was red, the second die was green. The first die was red, the second die was green. So a 1-5 is different than a 5-1. Okay, so now here's my lesser space, because I've limited what I can get. And now I'm going to ask the question, what's the probability of rolling a total of, let's say 5, let's say 4, given that the total is less than 7? There's 2 ways of doing this. One way, the way I don't prefer, is saying, well, it's the probability of getting the 2 things you want. So rolling a 4 and the total is less than 7. Oftentimes, one of these things just takes over here. If you want to roll a total that's equal to 4 and have it be less than 7, well, the only way for both of those things to be true is for the total to equal 4. Right? You can't roll a 5 and have it be equal to 4 and less than 7. You can only roll a 4. Sometimes there's more like grayness in the overlap there, but sometimes there's not. Divided by the probability of rolling a total less than 7. Okay, well, how many ways are there of rolling a 4 and a total less than 7? Let's see. There's a 4, there's a 4, there's a 4. Let's say there's 3 ways of getting a 4. And it being less than 7. So that's going to be 3 out of 36, because there are 36 total ways of rolling 2 dice, or rolling a pair of dice. Divided by the probability of rolling a total less than 7, which is 1, 2, 3, 4, 5, plus 4, plus 3, plus 2, plus 1, which is 15 ways. So 15 out of 36. But this is silly to do it this way. We already had the answer kind of, we almost just said it already. The probability we're actually looking for of rolling a 4, given that the total is less than 7, is the number of ways of getting what we want out of the total number of ways that make up our new world, or our new sample space, right? Because we start off by saying the sample space is like all 36 possibilities. Any 6 possibilities for the first die, any 6 for the second. But then, since it's conditional, we're saying we are given some new piece of information, and that limits our worldview. Our worldview is just this, none of the other stuff over here. And they say, okay, well, out of those 15 ways of something happening, there are 3 ways of getting what we want. And that's in my opinion, the better way of doing it, the more conceptually nice way of doing it. And that reduces to 1 out of 5. And we will definitely talk about that more on Tuesday.